Hello, in this video I wanted to talk about a pattern I observed among some mathematical models that involve matrices. Specifically, we can use matrices to describe transitions between states in a system with a finite number of states. In this video, I hope to make a connection between these seemingly different types of models and, as a result, shed some light on the matrix multiplication formula. Here's what I mean. Suppose we have some sort of system with a finite number of states. I'll call these states 1 through n, and we can associate these states with the basis vectors in an n-dimensional vector space. I'll use ei to represent the ith basis vector. General vectors will of course then correspond to some sort of combinations of these states. I'll denote the ith coordinate of a vector v as v sub I, and what these combinations and these coefficients represent will depend on our specific application. Then matrices will correspond to transformations of these systems, with the ijth entry of the matrix telling us something about the transition from state j to state I. Again, what it tells us will depend on the model. This might seem backwards, but it's because we apply matrices to vectors on the left, like function notation. We could flip things around, but that would require non-conventional notation, and that has its own disadvantages. Suppose we have a probabilistic system with n states. We can represent an unknown situation as a vector v with the coefficient vi being the probability of being in state I. Of course, these coefficients should each be between 0 and 1 and should together sum to 1. Then we can represent probabilistic operations on these systems as matrices, with mij being, if we start in state j, the probability of transitioning to state I. So in the example system below, we have two states, state 1 and state 2, and I've labeled arrows between them with the probabilities of transitioning from one to another when we apply some operation. For instance, if we start in state 1, there is a 0.3 or 30% chance of transitioning to state 2, which we see as entry 2,1 of our matrix M. Suppose we start out definitely in state 1, which we represent as just E1, and then apply our operation M. The result is a probabilistic situation where we have a 70% chance of being in state 1 and a 30% chance of being in state 2. If we're interested in what happens if we apply our operation again, we just multiply the result by our m again and do some linear algebra, here literally just distributivity, to ultimately get a 73% probability of winding up in state 1. And you can see why this works by looking closely at our linear algebra. This term here represents the probability of, if we start in state 1, staying in state 1. And we multiply it again by the chance of staying in state 1 again. And this term here represents the probability of going from state 1 to state 2, and then going from state 2 back to state 1. These are the two ways of going from state 1 to state 1 in 2 steps, and when we sum them, we get 73%. So in this situation, matrix composition corresponds to composing probabilistic operations. So the composition AB, remember that matrices are applied like functions, so matrix composition is also just like function composition from right to left. So the composition AB represents doing B first and then A. And looking at the matrix multiplication formula, we have that the probability of AB taking us from state J to state I is given by the following summation. For a given k, we take the probability that B takes us from J to K times the probability that A takes us from K to I. That's going to give us the probability of going from J to K to I. This gives us lots of different ways of getting from J to I, one for each K, and then we sum over all possible K to get the total probability of going from J to I. We can use linear algebra to study all sorts of things about these probabilistic systems. For instance, we can study the long-term behavior of these probabilistic systems just by taking the limit of matrix powers as p approaches infinity. Switching tracks, we can consider finite graphs as systems, where the vertices correspond to states and the directed and possibly multiple edges correspond to transitions. In this case, we represent these graphs in terms of their adjacency matrices. Matrices M, whose ijth entry is the number of direct paths from j to I. Then the entries of m to the p tell us about the number of paths of length p between various vertices. In the simple example graph below, we represent the fact that there are two edges from vertex 1 to vertex 3 by putting a 2 in the 3/1 entry of the matrix M. Then m squared will tell us about the paths of length 2. Specifically, there's 7 of them, all from vertex 1 to vertex 4, which we represent as a 7 in the 4/1 entry of the matrix M squared. This entry is the sum of the products of these two elements and these two elements, representing the two possible roots. In the first case, there's only one possible way of getting from vertex 1 to vertex 4 via vertex 2 in 2 steps. In the second case, we can choose from each of 2 possible edges from vertex 1 to vertex 3, and then we can choose from the 3 edges from vertex 3 to vertex 4. And we multiply that 2 and that 3, and then add on the 1 from before to get 7 total paths, which is exactly what the matrix multiplication formula tells us to do. We're not just getting the right answer, we're getting the right answer for the right reason. Proving that m to the p tells us about paths of length p is very easy by induction. In case p, our power, is 1, this is the definition of m. Note also that if p is equal to 0, then m to the p is the identity matrix, which tells us about paths of length 0. Then the inductive recursion comes from the matrix multiplication formula. If we're interested in paths of length p plus 1, we're looking at m to the p plus 1, or m times m to the p. And the ijth element of that, so the number of paths of length p plus 1 from j to I, is given by this sum. First, we multiply the number of paths of length p from j to k by the number of direct paths from k to I. This gives us the number of paths of length p plus 1 whose second to last vertex is k. Then we just sum over all possible second to last vertices k, including j and I, so this diagram here is a little bit abstract, to get the total number of paths of length p plus 1 from j to I. Now let's switch tracks again. We've seen how having different types of numbers, be they real numbers between 0 and 1, or natural numbers in our matrices, gives us different models. It's a bit of a leap, but if we're willing to use highly non-conventional numbers, we can reason very nicely about functions on finite sets and automata. Our motivation is this. What if we didn't care about how many paths of a specific length there were between any two vertices, just if there was a path at all? Specifically, if we already knew there was one path and we tried to add on another path, we'd like the result to say, there's a path, not there's two paths. In other words, let's let 1 plus 1 equal 1. Specifically, let's work with elements of the Boolean semiring, a structure with just 0 and 1, where addition and multiplication work as normal, except 1 plus 1 is equal to 1. You've probably actually seen this structure before in a different form. We can associate 0 with false and 1 with true, and then addition and multiplication become or and respectively. So 1 plus 1 equals 1 might more familiarly correspond to true or true is equal to true. This structure has all of the properties of a ring except additive inverses, so we can't really subtract and we can't really divide, which puts a bit of a damper on our linear algebra, but we can at least still make sense of multiplying matrices and vectors, and this genuinely is something that people do when studying automata theory. With these new scalars, our path counting becomes is there a path, with 0 for false and 1 for true. And if we look at our matrix multiplication formula, there is a path of length p plus 1 from j to I if there is some k, so we're going to OR over all possible k, we're going to sum over all possible k, such that there's a path of length p from j to k, and, that is multiplication, an edge from k to I. So again, just like before, we can prove by induction that m to the p sub ij tells us whether there's a path of length p from j to I. There's plenty of other uses for linear algebra over the Boolean semiring as well. Suppose we're considering functions on a finite set. We can represent subsets of 1 through n as vectors, whose ith coordinate is 1 if I is in the set. Then we can represent functions as matrices, whose ijth element tells us if f of j is equal to I, that is, if f takes j to I. And very nicely, using this notation, the matrix for f applied to E sub I will give us E sub f of I. So for example, if we have the following function on the numbers from 1 to 4, we can represent it as this matrix here. Then we can represent the set 1, 2, 4 as E1 plus E2 plus E4, in which case the product of the representatives of f and x will just be E3 plus E4, the representative of the image of x under f, the set 3, 4. So this notation lets us very naturally talk about the image of a set under a function. Note that since the images of 1 and 2 were the same, we had two summands of E3. If we were working in ordinary linear algebra, this would give us 2 E3, in which case we'd have some information about the image of f as a set with multiplicities, right? We'd have information that 3 was in the image twice. But because we're working in the Boolean semiring, 1 times E3 plus 1 times E3 is equal to 1 plus 1 times E3, which is just 1 times E3. So we don't get information about multiplicities. Instead, we just get the image of f viewed as an ordinary set. And there are pros and cons to both approaches. This perspective also lets us very naturally talk about pre-images of functions, since EI transpose times the matrix representing our function f gives us the sum of the pre-images of I. For instance, suppose we're looking at the same function and its corresponding matrix as we had before. Now if we let x be the set containing 2 and 3, the transpose of the vector representing the set times the matrix representing the function f gives us the representation of the pre-image of x under f, transposed. As an automata theorist, I'm interested in nondeterministic functions, functions that take in an input and have a set of possible different outputs, and our matrix notation for functions generalizes naturally. If you're familiar with relation composition, this is that as well, and if you're not familiar with relation composition, you can learn about it in the companion video to this one linked down below. We can represent these functions as matrices, where Aij again tells us if A can map j to I. It's just that now A can map a single j to multiple i's, so we can have more than one 1 in each column of our matrix. And again, the matrix multiplication formula describes composition of these functions. Applying b, then a, can take j to I if, for some k, again we're ORing over all k, b can take j to k, and a can take k to I. Furthermore, if we're thinking about these non-deterministic functions as relations, the vector ei transposed times the matrix for R times the vector ej tells us if j is related to I. And that fits in really nicely with our relation composition idea. This notation is excellent for reasoning about non-deterministic automata, machines where each possible input they could read transforms their state by some non-deterministic function. And you can do even better if you're willing to allow the entries of your matrix to be regular expressions. Instead of just being able to tell if a non-deterministic automaton can get from one state to another, you can get the linear algebra to spit out exactly the set of input sequences that take you from one state to another, as you can see in my video on paths, noncommutative formal power series, and row reduction, linked down below. We also use linear algebra to represent quantum systems. If we have a system that classically has states 1 through n, we can represent its quantum state as a complex linear combination of the classical states. The length squared of each of the coefficients represents the probability that when we observe our system, we will observe it in state I. So of course the sum of these probabilities has to be 1. Once we observe a system, its state changes to the pure state, the basis element of the state that we observed. Right? So we start off with a bunch of different probabilities of observing the various states, and then the observation affects the state, changes the state to just be the basis element corresponding to the state we observed. This is the Copenhagen interpretation. Other more natural and less solipsistic perspectives on quantum physics are also available, but the math is ultimately the same. Operations on the state of a quantum system are given by unitary matrices, matrices whose columns form a complex orthonormal basis. So, for instance, permutation matrices are unitary, and apply that permutation to each of the basis vectors in a superposition, that is a linear combination. Here our permutation matrix takes E1 to E3 and E2 to E1, and so takes a combination of E1 and E2 to the corresponding combination of E3 and E1. Unitary matrices are required to be invertible, so we can't apply an uninvertible operation to these systems. For instance, we can't delete data. If we take a look at this matrix here, when we apply it to a system, it takes state E1 to E3 and also E2 to E3. In effect, we've forgotten whether we started out in state 1 or state 2. That information has been deleted. But again, that's no good because the matrix that does this is not unitary and so doesn't represent a valid quantum operation. One of the tricky bits of quantum computation is working around this very strong conservation of information. More interesting is the situation where we have a unitary operation that introduces some quantum behavior. This Hadamard matrix here turns a system that's definitely in state 1 into a system that's in a superposition of a 50% chance of being in state 1 and a 50% chance of being in state 2. And it also takes a system that's definitely in state 2 to a system that's in a superposition of a 50% chance of being in state 1 and a 50% chance of being in state 2. This negative 1 over the square root of 2 coefficient is different, but it still represents the same probability. If we take the length squared of this coefficient, we still get 1/2. So let's go back to the situation where we've applied our Hadamard matrix once to the vector E1. And now let's apply it again to the result. The linear algebra gives us 4 terms, and here's the really cool part. The E2 terms wind up canceling each other out. We have 2 ways of winding up in state 2, one with coefficient 1/2 and the other with coefficient negative 1/2. And when we add them together, they cancel. And so there's actually no way to wind up in state 2. We definitely wind up in state 1. Somehow this combination of having 2 different ways of getting to state 2 cancels each other out. This is quantum interference, and it's the phenomenon that's happening in the double slit experiment. So as we can see, by changing up our coefficients, in particular changing up how adding them together works, we can produce lots of different behaviors that are useful in lots of different models. So thanks for watching. I hope this video helped draw some connections for you between widely different areas of math and got you interested in learning more. I also hope it helped give you a better intuition for what's going on in the matrix multiplication formula. Please leave any questions or comments down below and be kind to each other.